Well, hi, everybody. What I'd like to do today is give you a quick little example of a place where differential equations show up in the physical real world that we live in. In fact, differential equations are everywhere. And there are many examples that we could look at. The one that I'm going to focus on today involves a concept that you probably saw in calculus or in physics, relating position, velocity, and acceleration of an object to one another. And just as a background reminder, a differential equation, which I will often abbreviate DE, is just an equation that involves one or more derivatives of an unknown function. So there's some unknown function that is involved in an equation along with its derivatives. And generally the goal with these differential equations is to solve for that unknown function. That's generally what we would like to do if possible. So just to give you an example, I'm going to step up to my board here. And just to give you a quick example of this, suppose I considered the differential equation. I'm going to write it as y double prime of t equals g. And this little g is a constant. It's actually just a constant number. And let's imagine that if we were using the metric system of units, we might refer to it as 9.81 meters per second squared. Or if we're in the English system of units, we might use the number 32 feet per second squared. So both of those could be used. But the point is that g is a constant. And we have the second derivative of y as a function of t equal to g. So what you can observe here is that our unknown function in this differential equation, the unknown function in that differential equation is in fact y of t. And that would be the goal, would be to solve for that unknown function y of t. We would like to figure out what is that function. So this is my differential equation right here. It involves one or more derivatives of the unknown function y of t, namely the second derivative, okay, which is equal to g. Now, this turns out to be a good notation for studying the position, velocity, acceleration example. Because what I can do is I can imagine that y of t is the position. It's actually going to be the position of the object. There is some object that is in motion here. The position of the object at time t. We can imagine that that's y of t, the position. And our goal would be to find that unknown function, to find what is the location or the position of this object at any time, okay? But as you probably have learned in your calculus or physics courses, the derivatives of the position function are also very important. The derivative of the position, which is y prime of t, right? This is also known as the velocity of the object at time t. Okay, so we can talk about the velocity of the object. And if we go to the second derivative, y double prime of t, this is the acceleration. This is the acceleration of the object at time t. An object will generally be accelerating if it is experiencing some kind of a force. If there's a force on that object, you've probably heard of Newton's second law, F equals ma, right? The force on an object is equal to its mass times its acceleration, okay? I want to imagine for a minute that the object that we're thinking about is only feeling the effects of a gravitational force. So we have some object that only is, experiencing gravity as it, moves through space. If we have an object that is only experiencing gravitational force, then it turns out that its acceleration is exactly governed by this differential equation. The acceleration of the object is equal to a constant. Okay, so let's just write this down. For an object moving through space, subject only to gravitational force. So this object is only experiencing a gravitational force, right? In other words, this object is in free fall, right? Okay, so let me just add that here. Object is in free fall. If that's the case, if we have an object that is just in free fall, then its position is governed by the differential equation that we've already talked about on the board. Y double prime of t is equal to g. Okay, there are no other forces other than the gravitational force. Then the acceleration of the object is equal to a constant. This is, of course, just an approximation, but it's a pretty fair approximation to make. Okay, and also the g value, when we express it as a constant, that is, of course, when we're near the surface of the Earth. If we were near the surface of a different planet, or if we were pretty far up into outer space, this g value could, of course, be a very different number. So we're making an assumption right now that we're talking about an object that is falling in a free fall near the surface of the Earth, right? Something like what I'm doing right now with this marker. Okay. Now, I mentioned that the goal generally with differential equations is to solve them. And one of the reasons that I wanted to start with this example, guys, is because this is a really easy differential equation to solve. Y double prime equals a constant. Now, if you want, feel free to pause the video for a moment and think for yourself, how would you solve this differential equation that we're looking at in this box? And then in a minute, you can unpause the video and I'll tell you the answer, right? So let me give myself a little bit of space to do this. This is one that we can solve with very little training in differential equations. And that's because this is just simply something that can be solved by doing integration, a calculus concept, right? We can just simply integrate this equation. And I'm going to actually do this twice. I'm going to integrate this thing twice. So here we go. I'm going to integrate right here. The first time I integrate, I'm going to return back to the first derivative of y. Okay, so the second derivative of y, when I integrate it, I'll have the first derivative of y. And when I integrate a constant, which is g, it's just going to be gt. And then whenever we do these antiderivatives, we're simply going to have to remember to add a constant of integration here. So I'll call that plus c. Okay. And if I want to actually get back to y of t, then I'm going to have to integrate again. I'm going to have to integrate again. And when I integrate the gt part, of course, the integral of t is just t squared over 2. The g is a constant that I will make sure to write down. And then we have c times t. And there's another constant of integration that's going to come into play now. And I'm going to call this one d. So we have a quadratic expression. And that actually makes sense. If I was to sort of throw this marker through the space, right, it would trace the shape of a parabola as a function of time. So it's not surprising at all that that's kind of what we would expect to get. Okay, now, of course, this is many parabolas, right? Because there are different values of C and D here. Whenever you get a solution to a differential equation like we have right now, if it really is representing a family of solutions where there are constants that are sort of unknown values in the solution, this is called a general solution to the differential equation. In other words, there are many functions y of t that will satisfy our differential equation. And they are all sort of indexed over here by choices of C and D. If I change C and D, no problem. I still have a solution to my differential equation. If I take two derivatives of this, I will get G. Doesn't matter what C and D are. The C and the D are going to actually go away when I take two derivatives of this thing. Okay, so let's just write this down. This is what is called the general solution to the differential equation. It's the general solution. Now, if I gave you some additional information about this object, maybe where it was at a particular time or how fast it was moving at a particular time, we could actually figure out with that extra information what C and D are. We could solve for those constants if we had some what are called initial values. Okay, so let's just make a note here. If we are given what are called generally initial values, this might be something like y of 0 or y prime of 0, some extra information that we could incorporate into this general solution over here. Then what we could do is we could find the specific values of C and D, and this is what is called a particular solution. So the general solution is like this whole family of many, many possible parabolas in this case that solve our differential equation. But we can actually find a particular solution within this enormous family if we're given some initial values. So let's write that down. If we are given initial values, then we can solve for the constants. In this case, those constants are C and D. Of course, in other problems, there could be other constants or more constants. But we can solve for the constants in the general solution right? So we can solve for the constants that are in that general solution to obtain a particular solution. So there's a difference between a general solution and a particular solution. The particular solution is one specific solution where the constants have all been figured out. We know what C is, we know what D is, and so on. So a lot of times we will have a differential equation together with initial values. And there is a name for that. In fact, I'll put it here as a definition. A differential equation together with initial conditions or initial values. So either word is sometimes used, so I should emphasize that. So if we have initial conditions or initial values, so a differential equation A differential equation together with initial conditions or initial values is an initial value problem. It's called an initial value problem when it's a differential equation along with initial conditions. This is often abbreviated IVP, initial value problem. And when you have an initial value problem, the goal is generally going to be to find the particular solution. So I'd like to do an example of an initial value problem that involves the position, velocity, acceleration differential equation that we've already looked at. Let me give myself a little room to do that. Back up here to the top. So in other words, I'm going to give you a word problem. And the word problem is going to have the information that we need to find a particular solution to our differential equation. So here's an example, EX, for example, right? We're going to take a boy who is 2 meters tall. So a boy 2 meters tall. So this must be a problem that's going to use the metric system. Shoots a rocket, presumably some kind of a toy rocket, straight up at 10 meters per second. So that's actually an initial velocity, right? An initial velocity. So the question is, what is the highest point reached by the rocket? What is the highest point? How high does it actually go before it starts falling back towards the Earth again? Well, for the solution to a problem like this, what we have to realize is that, well, this is a position, velocity, acceleration example. The rocket is in free fall. And so we know that our differential equation is the one that we wrote down earlier, y double prime of t equals g. Now, in this example, we would use 9.81 as an approximation for g because the problem is being given in the metric system of units. However, I'm just going to leave g in my calculations as I go along. I don't need to necessarily put in the 9.81 at this stage, okay? Now, we've already integrated this twice and come up with the general solution. So I'll just write it down one more time here, but this we have already done. The general solution is just obtained by integrating twice. 1/2 gt squared plus ct plus d. This is the general solution to our differential equation. However, we need to figure out the particular solution that matches the given information here. Just to help me kind of think about this, I'm going to draw a picture here of this boy. I'm just going to do a little stick figure, okay? And this is 2 meters here. The boy is 2 meters tall. And presumably he's going to, let's just put his hand right here. He's going to start at the top of his head, basically, and he's going to throw this rocket up, and it's going to come down like that. This is just a visual of what's going on. Now, we have to make some conventions about where our coordinate system is set up for a problem like this, okay? For example, just to give you one idea of something, remember that g, as I mentioned a moment ago, g is 9.81 meters per second squared. Now, I have written that as a positive number, but of course I realize that the acceleration is towards the Earth's surface, right? In other words, the object eventually gets sucked down towards the center of the Earth. What this means is that the acceleration of gravity actually points this direction. So I have two choices. I can either make this 9.81 into negative 9.81 if I want to use positive as my orientation. Or the other alternative is to just decide now that the downward direction will be positive. And that's actually what I'm going to do. So this 9.81 is with the assumption that downward is positive. And why that's important, for example, why is that important? Well, when I look at my initial values, I'm saying the rocket is shot straight up at 10 meters per second. So when I think about shooting the rocket upwards, let's write down our initial values, right? What that basically is telling me is what is the velocity at time 0 when the rocket is first launched? The answer is going to actually be negative 10. And the negative is because I have decided that downward is positive. I've made that decision and I've got to stick with it now. And this implies that a velocity that is upward oriented is in the negative direction. Now, I should just pause for a moment and let you know that it's somewhat arbitrary that I'm deciding that downward is positive. I could flip everything over and I could say upward is positive. That would make my 9.81 negative, but it would make the negative 10 positive 10, right? So you can flip the signs of these numbers by flipping the direction of your orientation. The other thing that you have to keep in mind is we have to figure out where exactly is the position of 0 going to be set up at. A natural place to do it would be the ground. Wherever the ground is, that's going to be y equal to 0. And then we would orient anything under the earth would be considered positive position, and anything above the surface of the earth would be in the negative direction. Because remember, I'm going to do a downward orientation to my y-axis. Downward is positive. Turns out that just to make the calculations come out easier, a really good choice for how to set up your y-axis is to set y equal to 0 to be exactly at the position where the object is going to start. I'll say that again. The best way for the purposes of calculation to make the things come out simple, as we're going to see in a minute, is to set y equals 0 to be exactly at the horizontal position where the object starts from. So I am going to take y equal to 0 to be right at the top of the boy's head, and I'm going to use a downward orientation of positive. Now, why does this make sense? Why not just use the ground as my initial position, or as y of 0 equals 0? I can do that. Remember, this is kind of an arbitrary choice again. Like where I choose to start measuring my y value is up to me. And different people might do it differently. But the reason that it's kind of nice to do this and to set up y equal to 0 at exactly the place where the object is going to start is that that will always result, whoops, not the derivative here, that will always result in an initial position y of 0 equals 0. It just makes things nice. Y of 0 is always equal to 0. So this is always true if the y-axis is set up as described over here. Okay? So if we set up the y-axis so that the 0 value is exactly at the position where the object starts its trajectory, then y of 0 will be 0. And what we're going to notice is that that makes our calculations kind of nice. Because if I go back to the general solution and I plug in 0 into the position function, y of 0, everywhere I see a t, I'm going to put a 0. Notice that I just get d. Y of 0 is just equal to d if I put in 0 for t over here, right? And so d is therefore 0. So if you set up your coordinate system this way, guys, d will always be 0. That's the beauty of it. Okay, great. So we have d is equal to 0. And then also I'm going to look at the derivative. Well, maybe what I should do over here is I should take the derivative here, y prime of t. We did this earlier, but just to get it back on the board again, the derivative of y is just gt plus c, right? If I plug in 0 for t into the derivative, I just get c. And we were given in this problem that that was equal to -10. So we solve for our constants by using the initial conditions. And so this gives us now our particular solution. Our particular solution is y of t equals 1/2 gt squared minus 10t. And there's no constant term because d was 0. So this is it. This is the one and only parabola that describes the motion of this rocket as it is launched into the air. So far, I haven't even addressed what the question is asking. I just wanted to figure out the particular solution here. Generally, if you've done that, you'll be able to solve everything else that you want, right? We not only know the position of this object, we also know its velocity, right? It's just gt plus c, which is just gt minus 10. So it's kind of nice, guys. At this point, I now know the position, the velocity, and the acceleration of my object. I should be able to answer any question about this object that I want. Question is, what is the highest point reached by the rocket? If you think about it, that at that highest point, what is special about that highest point in terms of the motion of the object? If you think about it, the velocity of that object right at the apex of that trajectory, the vertex of that parabola, right? That velocity will be 0. And if I set this velocity equal to 0, right? So if I set this velocity, if I set this equal to 0 right here, I can figure out what time it was. We have gt minus 10 equal to 0. I can figure out at what time the rocket reaches the highest point. That's the time right there, at that time. And so once I know the time that this is happening at, hopefully I can now find, well, what is the position of that object at that time? What is that highest point? So I'm actually going to plug this value of t into the position equation now, right? In fact, let me come right down here so that I can do that. If I look at y of 10 over g, remember, I'm just going to leave the g in the calculations here. So I'm going to just calculate the position at that time. And what I'm going to get is 1/2 g times 10 over g squared minus 10 times 10 over g. We're just putting in 10 over g for the time everywhere that we see it. And what you will notice when you actually simplify that calculation is that this comes out, I will let you guys check me on this, but it comes out to negative 50 over g. This would be in units of meters in this particular example. But we might be a little bit confused about getting a negative answer here until we remember how we had set up our coordinate system right here. Y equals 0 was here. And the negative direction actually goes up from that. And notice that this position here is already 2 meters above the ground, right? So if we wanted to know the height above the ground, what we would need to do, guys, is adjust this answer just a little bit. How far above the ground is it? Well, all of that 50 over g is in the upward direction, right? Above this y equals 0 line. And there's another 2 meters of distance between the ground and the top of the boy's head. So this is actually going to be the height above the ground, 50 over g plus 2. And that's in meters. It's always good to label your units on a problem like this. So there you go. We have the height of this rocket above the ground at the highest point. Let me just ask one quick follow-up to this question, as long as we're thinking about it, just to kind of give us a little bit more practice with this. Let's suppose that we ask the second question, which is when does it hit the ground? So let me phrase this right here as a follow-up. Follow-up, when does the object hit the ground? If you want, you feel free to pause the video if you want to think on it yourself for a minute. And then I'm going to go ahead and jump in and help us think about this. Now remember, I erased my little picture, didn't I? But remember that the ground is actually plus 2 units. It's down 2 units from where we set up our y equals 0. So the idea here is that we're going to want to know when does the object have a y value, a position of 2. That's exactly what we're going to be trying to do. So here's my position equation. 1/2 gt squared minus 10t equal to 2. And this is really just a quadratic equation, right? It's just a quadratic equation. I can actually rewrite it in a more standard way by just subtracting the 2 over to the left side. This is just ax squared plus bx plus c, basically, right? And so we can solve for t. Remember, t is the question. When? When? It's always important to read these things closely. What are they really asking for? They're asking for when, which is a time. So we can solve this for t using the quadratic formula. So we can use the quadratic formula to solve for t. Okay, so let me just do that really quickly. We take the negative of negative 10, which is 10, plus or minus the square root of 10 squared, which is 100, minus 4 times this guy, which is actually going to give me plus 4g, I believe, if I did it all right, all divided by 2. Oh, sorry, all divided by 2 times 1/2 g, I should say, which is g itself. We're going to get something like that. Okay, so we get this expression here so far, and you could consider this a final answer. Now notice that there are 2 values of t here. And one of them is actually negative. If we somehow could take the rocket out of the boy's hand and reverse time to before he launched it, we would get some negative value of time when the rocket was on the ground. However, what we're much more interested in here is coming up with a positive answer. So to do that, we just want to take the positive value, and that would just simply be 10 plus the square root of 100 plus 4g all over g. And with a calculator, you can, of course, get a specific numerical value, but I am much more interested right now in just the process, and leaving g in your answer would be totally acceptable to me. Anyway, I hope that this video makes relatively good sense. The acceleration differential equation is very simple. Y double prime equals g. We integrate that twice to solve it. And then if we have initial values, for example, if we have a word problem that has some numbers we can plug in, then we can solve for the constants in the general solution and use the particular solution. Here's the particular solution right here. We can then use this as our primary tool to answer any additional questions that might come up. I hope the video has been helpful. I hope you enjoyed it. If you have any questions for me about this, by all means, I really do hope that you'll reach out. I'll be more than happy to give you a hand. That's all I got for now, everybody. Please take care. Thanks for being here. I'll see you again soon. Bye for now.